Okay, so let's continue. A few classes ago, first of all, let's try to understand where we are right now. All right, a few classes ago, we said goodbye to electricity and we moved to the world of magnetism, right? And when we moved to world of magnetism, what we've done? First, we introduced all possible ways of finding magnetic field. It's one of the essential quantities, of course, in electromagnetism in general, right? So we introduced Biot-Savart law, Ampere's law, so those two options which can be used to find magnetic field. But that's not complete story, right? In order to have a complete story, we introduce magnetic forces. So basically, they tell us the magnetic force tells us how those fields interact with the material, and that's what we've done in the previous class. We introduced magnetic force. Magnetic force on a point charge. It's one of the fundamental equations in physics overall. Right, it's called Lorentz force. F equals Q times V cross B. And then, as a consequence, short derivation, short transition from that formula, we can move using small derivations. We can move from that formula to the formula for the magnetic force on a wire with a current. So we used those formulas in the previous class, in the previous recitation class, and to solve this or that problem. Now, let's look deeper into the fundamental formula for the magnetic force. F equals Q V cross B, and see what we can get out of that formula, right? Probably first, I will write that formula over here, and then all right, so we're going to play with this formula today. V cross Q times V cross B, right? And let's look at two situations. First, let's assume that charge travels along along magnetic field lines. Let's assume, for example, magnetic field lines, magnetic field points that way. And for example, something like this, right? So let me put first a small bullet over here, right? First situation. All right, so if we have magnetic field lines pointing this way, right? So let's say this is B. And let's assume that we have some charged particle, and positive or negative, it doesn't matter. Let's say we have charged particle Q traveling with velocity v in that direction. Of course, we all know that we can find magnetic force. Since there is a charge exposed to the magnetic field, there must be some magnetic force. Okay, let's calculate this, right? So absolute value, I will look immediately at the absolute value. Q V B times sine of angle between these two vectors, V and B. What's the angle between those two vectors? 0 degrees, it's obvious, right? 0 degrees. As a result, force acting on the particle in this case is 0, and it means that this particle experiences 0 magnetic force. So it means that this particle is going to travel along a straight line forever and ever, since the net force acting on the particle is 0. So we're going to have just a motion along a straight line. Right. So a Q travels along a straight line. Okay, I will separate it. It's our first situation, right? And now let's look at a different situation. I will put a new bullet, and then in a few minutes I will write the title, right? But first, let's turn everything by 90 degrees. Okay, not everything, but direction of the magnetic field lines. All right, so let's assume that, for example, our magnetic field lines are into the board. Into the board, it means we can draw crosses. So let's assume that we have these. So these are our magnetic field lines. So that's B, right, into the board. And now our particle is going to travel perpendicular to these magnetic field lines. Again, here you see charge travels along the magnetic field lines. Now let's assume the charge travels perpendicular to the magnetic field lines. Now, for example, let's assume that we have charge Q here and it travels this way. So that's velocity V. So what are we going to have in this case? Force. Let's first see direction of the force. Q, V cross B. Let's assume for simplicity for now that this charge is a positive charge, right? Then direction of the velocity, direction of the force is determined by the direction of the cross product V and B. Okay, V. So we just need to find direction of the cross product. We know right-hand rule, right? V that way, B is into the board. We can apply right-hand rule, V cross B. As a result, direction is that way, right? So that will be direction of the force. So this will be F direction of the magnetic force acting on this particle in this situation. And now let's try to imagine which trajectory this particle is going to experience. Velocity that way, so basically that is the direction of motion of the particle, right? You remember direction of the velocity give us direction of motion. So particle tries to travel this way and the force is perpendicular. Which trajectory are we going to have? When they are force all the time perpendicular to the direction of motion. We've seen this motion in physics 1 many times, right? We describe that motion. It's a circular motion. It's a circular motion. Circular motion, right? It's sort of like a, for example, motion of a satellite around the Earth, right? So we have the Earth, satellite orbiting, let's assume circular orbit, and every time force, gravitational force in that case, is perpendicular to the trajectory, to the circular orbit, right? So here, similar situation, but of course the nature of the force is different. In the case of a satellite, that is a gravitational force. Here we have magnetic force, but trajectory the same. So now let me draw a trajectory. Okay, I'll try to draw a circle. Right, so we have a circular orbit, okay, slightly distorted. So this will be the center, right? And so now we need to describe this trajectory, right? And what can be used in order to describe any motion? In physics 1, we used it a lot. Newton's second law. Newton's second law is an equation of motion, right? If you want to describe motion of any system, in this case, charged particle, we can apply Newton's second law. All right, and okay, before I start applying Newton's second law, this motion is called the cyclotron motion. So now I'm ready to write the title on top of this, right? So that is cyclotron motion. Let me label it cyclotron motion. Right. Okay, so that is the cyclotron motion. And now I want to, as I said, I want to describe this trajectory. And since it's a circle, description of the trajectory is quite simple. We just need to find the radius. Once you know the radius of the circle, you know everything about that circle. Right. So we're going to apply Newton's second law. Newton's second law. Of course, F equals, okay, it's a vector. M times acceleration, because we have basically two-dimensional motion, right? So it's not the motion along a straight line. So we have a motion in a plane. It's a two-dimensional motion. All right. So we'll have to look at two components. And so we'll have to apply Newton's second law. And which force acts on the object? Our Lorentz force. So let's write explicitly that formula. Let's write explicitly the formula in the direction. Right? So I will write underneath F equals Q V cross B. And first I want, basically that's what we're going to use in our Newton's second law. And first I want to find a direction of this force. Direction of the force. Okay, before I write direction, let me introduce coordinate system. Again, let's recall in physics 1, when we describe circular orbits, we introduced not just x and y coordinates. We used r and t, right? You can easily recall it, right? So t, it's a tangential axis along a tangential direction, right? So that's t, and r is radial direction and towards the center. Why we picked radial axis towards the center? Because our centripetal acceleration is towards the center, and in order to have that acceleration positive all the time, it's better to choose our direction towards the center to make centripetal acceleration positive. Right. Okay, and now with these coordinates, and you see again they are perpendicular, like x and y, but in this case we don't use x and y, we use t and r, right? Okay, so now you see direction of the force is radial, right? Direction of the force is radial. We discussed already. So r hat direction, radial direction. Then absolute value. Let me write the magnitude. F equals Q V B, and sine. What is angle between V and B? V that way, B into the board. The angle between them is 90 degrees, right? Their angle was 0, now it's 90 degrees. Sine of 90 degrees. Sine of 90 degrees is 1. So, as a result, absolute value of the force is QVB. So, now we know direction, we know absolute value, and now let's apply Newton's second law for both directions, T and R, right, in order to have a full description of this motion. Okay, so now, which direction should I apply first? Probably T. Let me get T direction. You see, T means tangential direction. In the tangential direction, Newton's second law, F equals to 0, because we have only one force, magnetic force, and that force acts along the radial direction, along R direction. In the T direction, we don't have any force, F equals 0. As a result, our Newton's second law, MA equals to 0. MA equals to 0, and as a result, acceleration 0, and velocity is constant. As a result, V is constant. So we have what? We have basically uniform motion. So this particle travels along this circle with a constant speed. So basically we have uniform circular motion, right? Okay, that's what we can get from T direction. As a consequence of the fact that we don't have any force acting in a tangential direction. But in the radial direction, we have our magnetic force. So let me put now R direction. And now Newton's second law, force in the radial direction equals mass times acceleration in the radial direction. And of course, you all know which acceleration I'm talking about. It's a centripetal acceleration, right? Centripetal acceleration. It's acceleration which describes how fast direction of the velocity changes in time when particle travels along a circle, right? Physics 1. Okay, so now we know absolute value of the force. It's QVB in the radial direction, and we know the formula for the centripetal acceleration. So we can easily write now QVB equals mv squared over r. R, it's a radius of this circle. Okay, since we're talking about cyclotron motion, usually we add subscript SYC, cyclotron motion, cyclotron radius, and I will also add that. Okay, so now this can be easily solved for radius of this trajectory of this circle. Something can be cancelled, 1r can be cancelled, and as a result we're getting the radius of this formula, a formula for the radius of of the circle, right? Cyclotron motion. So R cyclotron equals mv divided by qb. M times v divided by charge times the magnitude of the magnetic field, right? So cyclotron radius, I can write it cyclotron radius. Usually on I don't give this formula on a formula sheet on the exam, right? Every time I expect from students to get through this half a line derivation, right? It's quite simple. So as a result, yeah, we have circular motion with constant speed of the particle. So we have uniform circular motion. Now, I guess let's look at some special cases. Let's assume that, for example, let's say magnetic field. What if magnetic field is zero? What if magnetic field is zero? Of course, we know if the magnetic field is zero, this particle is going to move along a straight line. Are we going to get straight line from this formula? If b equals zero, let me write so. If b equals zero, since b is in the denominator, it will make r cyclotron infinite. So r cyclotron equals to infinity. Okay, which trajectory has a infinite radius? It's a straight line. Right? So straight line. So it makes sense, right? So we know from our everyday experience, so in this case, we're going to have a straight line, and we're getting straight line from the formula. Okay, it makes sense. What else? Okay, so next, basically we describe this motion, and now additional stuff. Let's find the period. So basically we have a periodic motion. So this particle is going to circle around this trajectory almost indefinitely, right? So let's find the period. What is period? What is the period by definition? It's a time a particle takes to complete one circle. It's just a time to complete one circle, right? Usually at this point, if I ask a question like this on the exam, many students basically panic, right? And as a result, lots of nonsense in the solutions. But this case, the explanation is quite trivial. Explanations are quite trivial. For explanations, I went to get my ruler, flexible ruler. Okay. In order to understand what needs to be done over here, let's start with this. Let's assume I have this flexible ruler, right? And let's assume that we know this distance, and we know that the particle or bug travels along this distance with a constant speed. And if I ask you, what's the travel time? The question is banal. You just take the total distance and divide it by the speed, constant speed of this particle, of this bug. So you will get the travel time. But if I bend it, in the same condition, let's say we know the distance, and we know that particle travels with constant speed, or bug travels with constant speed. What's the travel time? Exactly the same, because we still have uniform motion. We have a constant speed. So you take the total distance and divide it by the speed. And if I keep bending my ruler, right, and in the limit, of course, I can end up with a circle. But let's assume we still have uniform motion. It means that let's assume that we still have constant speed. Bug still travels with a constant speed around this circle. So how can we find the travel time? Circumference divided by the speed. Because the key word is we have uniform motion. Uniform, it means constant speed. It doesn't matter how complicated your trajectory is. If you want to find the travel time, the total distance divided by that constant speed. Because the motion is uniform, and that's what we have here. We have uniform circular motion, right? Okay, so as a result, period, which is the travel time along the to complete one circle. So it's a 2 pi r, which is circumference, divided by the speed. So the period, let's find the period, right? So I can write so t, and again I will add subscript cyclotron, right? So 2 pi r cyclotron divided by the speed divided by v, right? Cyclotron we just derived, so it will be 2 pi over v. It's a 2 pi over v, and now I'm going to, okay, it's too big, and now I'm going to multiply by the formula for the cyclotron radius, mv divided by q times b. And you see, velocity gets cancelled. As a result, we have the formula, right? 2 pi m divided by q times b. And again, on the formula sheet, I will never give this formula, right? Because I expect you can easily derive this, and then simple logic can gives you this formula, right? It's not, these formulas are not fundamental, right? They can be easily derived from fundamental stuff, like Newton's second law and Lorentz force, magnetic force. Okay, what is interesting, period does not depend on the velocity. It means what? It means this, right? So if a particle has, let's assume particle has a small velocity, right? As a result, it will have a small cyclotron radius. So basically, it will travel along the small circle, and as a result, also small the circumference. So small circumference, small travel distance divided by the small speed. As a result, we'll get some period. But let's assume particle travels faster. Particle travels faster. As a result, cyclotron radius is larger, so it will travel over a bigger circle. Bigger circle, larger circumference, so larger travel distance. Larger travel distance divided by the larger velocity, and we're still getting the same travel time, right? So smaller speed, smaller circle, larger speed, larger circle, but the ratio of the circumference over the speed is exactly the same, and that's what we have. That's our period. So now, once we know the period, we can easily get, for example, frequency, right? Okay, I'm not going to write a new line. I will just write over here. Of course, we all know that frequency equals, it's a reciprocal of the period, right? So we just flip this, it will be QB divided by 2 pi times mass. Yeah, I can also add subscript cyclotron. Okay, so that's important addition. And now we have these two special cases. Particle travels along magnetic field lines, particle travels perpendicular magnetic field lines. But now let's assume that we have a situation where we have superposition of these two motions. How? Okay, it's very easy. Right? Let me probably write something like this. Let's combine these two motions. Let's combine these two motions. Right? Why not? Okay, so now let's assume that we have some magnetic field lines, for example. Let me get this way. Right, so these are, for simplicity, let's assume still uniform magnetic field. So that's B. And now let's assume that our particle enters this magnetic field neither parallel nor perpendicular to the magnetic field lines. Let's assume that it enters at some, let's say, for example, strange this angle. Let's assume that this is velocity v, right? And it enters this way. So how can we describe motion of the particle in this situation? let's just decompose this velocity. We can easily decompose this velocity into two components, parallel to the magnetic field lines, and we know the behavior of the particle, and perpendicular to the magnetic field lines. We also know the response of the particle. And then we'll just have to superimpose these two motions in order to get the resultant motion. Okay, so let's decompose. So this will be, let's say V. Let me label it. Let me write it better. V parallel. So component of this velocity parallel to the magnetic field lines, and perpendicular component V perpendicular, right? And so we know what happens with this velocity, nothing, right? So this velocity will stay the same. As a result, this particle is okay, let me write also Q. It's a particle Q, right? So this particle is going to experience a uniform translational motion along the magnetic field lines, right? But on top of that, this component perpendicular to the magnetic field lines is going to give us this circular motion. So as a result, we have circular motion because of this perpendicular component, like this, right? And uniform translational motion along the magnetic field lines. As a result, basically we have something like this. We have helical motion, just helical motion. Basically, a particle is going sort of like a spiral around magnetic field lines, right? So as a result, we can draw something like this, right? Right, so we're going to have something like this, right? So we have helical orbit, helical motion, right? And one parameter which we will need for the next problem is this distance, right? You see this distance. It's called the pitch, right? So P. I'm thinking where can I write pitch, right? So this distance, pitch for this helical motion, right? Okay, and now enough of writing. Now there are tremendous consequences of this simple motion, right? Because of this simple motion, helical motion, we are still alive on this face of the Earth. Why? We have the sun, right? There are lots of processes happening on inside of the sun, right? And as a result, the sun produces tons of high energy particles, and those high energy particles, they travel in space in all possible directions, and of course some of them travel towards the Earth, right? They have very large energy. As a result, if you put any living creature like human body, right, in the direction of those particles are going to damage the molecules and so on, and basically the life will be over very soon, right? So these dangerous particles travel towards the Earth. And what happens, right? They're not killing us. Why? Because when they start approaching the Earth, you remember, has a magnetic field. And there are, of course, these magnetic field lines, right? So in those particles, they enter magnetic field lines at a certain angle, right? And those high energy particles start circling around those magnetic field lines. And you remember, magnetic field lines, they sort of start on the North Pole and end at the South Pole, right? As a result, those particles starts circling around those magnetic field lines and starts traveling towards the poles, right? Positive in one direction, negative in the opposite direction, right? So as a result, they move towards, for example, let's say some particles travels towards the North Pole. Instead of traveling towards the Earth, right, directly they start traveling towards the for example, the North Pole, making this experiencing this helical motion, right? And then when they first enter when they first start experiencing feeling magnetic field lines, they're reasonably far away from the Earth, where the atmosphere is where there is no atmosphere. But when they start coming closer and closer to the North Pole, for example, right, they enter the Earth atmosphere, where tons of molecules, and of course these high energy particles starts colliding with hydrogen, nitrogen, and tons of other molecules, right? So they collide with these molecules, and those molecules, after collisions, they produce light. That's why if you are closer to the North Pole, you see this beautiful phenomena, the northern lights or aurora, right? That's the explanation of that light, right? Of course, some students ask at this point, come on, does it mean that it's dangerous to be at the poles? No. There's a more complicated phenomena, right? So when the particles are getting closer and closer, for example, to the North Pole, magnetic field gets stronger and stronger. Magnetic field gets stronger. As a result, the radius of the cyclotron motion is getting smaller and smaller. Particle travels faster and faster and faster. As a result, there is a additional, more complicated effect. Basically, particle gets reflected. So first it travels towards the North Pole like this, but then it stops for a moment and starts experiencing helical motion in the opposite direction. So basically, it will travel back and forth between the poles, losing energy, and till the moment when they are just harmless. All right? Okay. So this simple physics, or maybe not so simple, explains why we're still alive on the Earth, right? Because those high energy particles can easily kill any living creature, right? And also it explains the northern lights. Okay, enough of this. And now tomorrow in my lecture I will look at some other applications of this cyclotron motion, right? But for now it's enough. Now let's solve a couple of problems related to cyclotron motion. Okay, so let's look at problem 65 from the book Problem 65. So what do we have here? We have magnetic field. For simplicity, we're going to assume that that magnetic field is uniform, and magnetic field lines, let's assume, point upward, right? And then, so the value of the magnetic field strength is given. And let's assume that we have some particle. Actually, the particle is an electron. Enters those magnetic field lines at a certain angle. Angle is given, right? And we will have to describe that motion and find something about that motion, right? Okay, let me start with a picture. So let's assume that we have our magnetic field. Okay, not assume, it's given. Magnetic field lines are vertical. Let me estimate space. All right, so let's assume that these are our magnetic field lines, right? B, right? And then before I draw particle, before I introduce particle, let me introduce coordinate system. Right, so I can introduce coordinate system any way I want. Let me align z-axis along my magnetic field lines. So let's assume that this is our z-axis, right? And let's say this is what, y, and this will be my x and y, right? Okay, and now particle. So let's assume that our particle enters this magnetic field. So let's say it's an electron. Let me write explicitly, it's an electron. All right, so we have a charge, we have a mass of an electron, so it enters the magnetic field in this direction. So this is V. Okay, magnetic field is uniform from that infinity to that infinity, right? So enters this magnetic field at the angle, let's say this angle theta, which is, okay, you know what, I will probably write on top. So let me just write theta. Theta is 30 degrees above xy plane. 30 degrees above xy plane, and for simplicity I just align along sort of along y direction, right? Sort of right now it's in zy plane, right? We're not losing generality of the problem. And the absolute value of the velocity is also given. V is 5 times 10 to the power of 6 meters per second. Yeah, and also the magnetic field strength is given 30 millitesla. Right? So now, before I write what needs to be found, I want to describe the motion, right? I want to describe, I want to describe the motion, and only then I will be able to write what needs to be found. Right. So let me check if I mention everything. All right. Yeah. Okay. But before, let me describe trajectory. So we have particles. We have a particle entering the field at this angle, right? And it's neither parallel nor perpendicular. But we can easily decompose this magnetic or this velocity and find components along the magnetic field line and perpendicular, like we've done here, right? Yeah. So I can find, for example, this will be my, let me label it as, let me use blue because these velocities are so important. Let me use blue. So this will be V in Z direction, right? Although the nature of this velocity is parallel to the magnetic field lines. Okay, not the nature, but the major feature. And the second component will be V sub Y. All right. Again, the major feature of this velocity is that it is perpendicular to the magnetic field lines. And we know what is this velocity going to give us, and we also know what this velocity is going to give us, right? But first I will just write so we can decompose. V equals to Vy plus V sub Z, right? And of course, probably I will write underneath because I need, or maybe I will be able to squeeze it. Let me write so V Y. Of course, how can we find V Y? It's a V times cosine. V times cosine of angle, right? You see this triangle, a right triangle, and we're finding the side which is adjacent to the angle theta, cosine, right? And this component is perpendicular to the magnetic field line, perpendicular to B, right? And which trajectories are we going to get from this velocity? Cyclotron motion. We're going to get a circular motion, cyclotron motion, right? Which we wrote. Okay, I wrote uniform, or a cyclotron motion, right? So this component of the velocity is going to give us cyclotron motion. Basically, we're going to get a circular orbit, right? And V sub Z this component, what can we find it? Yeah, of course, v times sine of theta. V times sine of theta. So that's the absolute value of this velocity. And of course, that is velocity which is parallel to b. Again, that was perpendicular to b, now it's parallel to b. And this component of the velocity is going to give us just the uniform translational motion along the magnetic field lines. So we have uniform translational motion. Translational motion. So the particle is going to move along the magnetic field lines with this velocity forever and ever, right? And this cyclotron motion, you remember, it's a uniform circular motion. So it means the particle is going to circle with this velocity v sub y, circle with velocity v sub y. So it's a uniform circular motion along the circle with a constant speed, right? Speed. Right, so as a result, we have superposition of these two motions, cyclotron plus uniform translational motion. We're going to get a helical motion along the magnetic field lines. So we're going to get something like this, right? Let me draw it, right? Something like this, right? Okay, and now I can write what needs to be found. So we need to find the radius of this this helical motion, or the radius of the cyclotron motion, basically, right? And we need to find the pitch, which I mentioned over here, right? It's the distance between this point and that point. So that's what we need to find. So now I'm ready to write find our cyclotron, and then second we will have to find the pitch, right? So which is this distance? So that's p, right? Yeah, and cyclotron I can draw here, of course. That's our r cyclotron. That's what we need to find. Okay, let's start with a cyclotron radius. I will put a small bullet, and of course you can just grab this formula and plug numbers. I don't like this, right? I want to start again with the Newton's second law in the radial direction, right? So, right, Newton's second law, r direction, radial, right? So I can write that we have Fr equals mass times centripetal acceleration, right? Circular motion. And what's the value of Fr? Fr, it's our magnetic force. Magnetic force, which is QVB, right? Because again, but you know what? Let me write it this way. So Q and V, and I stop for a moment. Which velocity? Not the total velocity v, no. This is the magnitude of the total velocity, which consists of two parts, v sub z and v sub y. V sub y is because you remember it's a component perpendicular to the magnetic field. Only this velocity is responsible for the cyclotron motion, So we have to use here v sub y, not the total v. So q v sub y times b, and times, of course, sine of 90 degrees, right? Vy b sine theta, right? Okay. And of course it is equal to mass times, okay, centripetal acceleration. V again, v sub y squared, because that's the component of the velocity involved in this circular motion, divided by r cyclotron, right? So, of course, this is 1. Then v sub y, 1 v sub y can be cancelled, right? As a result, we're getting the radius of cyclotron motion. Mvy, mv sub y divided by q times b. Basically, we got this formula, right? But instead of just v, we have v sub y, right? So that's the final, okay, not the final to find the cyclotron radius. And now if you plug the numbers, right, so I can write mv, instead of v sub y, I can write v cosine theta divided by q times b, right? Okay, so if you plug numbers, you are going to get 0.82 millimeters, less than a millimeter, slightly less than a millimeter, right? So next, what's next? We need to find pitch. But you know what, before we can start discussing the pitch, let's find the period of cyclotron period, right? Basically, the time a particle needs to complete one circle. We just discussed, right? So it just since we have a uniform circular motion, again, uniform, it means that the speed of the particle is constant. So you just total distance, which is circumference 2 pi r, divided by the speed. Again, in our case, it's v sub y, right? V sub y. So the period will be t cyclotron equals 2 pi r cyclotron divided by v sub y. Okay. So v sub y, again, it's a v times cosine theta, or you can, we could have calculated it immediately right over here, right? Because theta is given 30 degrees. So you can get the absolute value of v sub y. And you use it here. So if you do that, you're going to end up with 1.19 times 10 to the power of minus 9 seconds. That's slightly more than 1 nanosecond. So the period is very, very short. So particle travels very, very fast, right, over the circle with this small radius. So it circles fast. And now we can find the pitch. Finally, now we can find the pitch. So now you need to understand that here we have superposition of two motions, right? This circular motion and uniform translational motion, right? And if time to complete one circle is t cyclotron, right? Time to complete one circle. What happens with the particle in terms of motion in z direction? It moves from this point to that point over this period, over this time, right? Because time links these two motions, this motion around the circle and motion, uniform translational motion in z direction. They're linked through what? Through time, through this universal parameter, right? As the particle makes one circle in cyclotron motion, right? In this direction, because it still travels with this velocity in z direction, v sub z, it will complete this distance p. All right, so p will be equal v sub z times the period which we just found, right? So as a result, pitch, we can write, which way I wrote. Okay, probably before writing the formula, I will write this. Over this time t, cyclotron, electron travels in z direction distance p. Okay, over this t cyclotron, electron travels in z direction, in z direction, distance p, distance p, right? Okay, as a result, I can write, so the pitch equals v sub z, which again you can easily find by multiplying v and sine theta, times t cyclotron, right? Okay, so it will be v times sine of theta, sine theta times t cyclotron. Again, so everything is found, so you just need to plug numbers and you will end up with 3 times 10 to the power of minus 3 meters. Right. So 3 millimeter, right? So 3 millimeter in this radius 0.8 millimeters, right? And the period is slightly more than a nanosecond, right? So that's the problem 65. Basically, it's related to this helical motion, right? So next, some easy problems. Actually, these are no. This is one question. This is conceptual question 6. Conceptual question 6. And there are two parts, A and B. So let's discuss that. So let me write something like this. Conceptual question 6. And first part A. Part A. Okay, so let's assume that we have a uniform magnetic field into the board. So it means that I can use crosses to show this magnetic field. And again, we are going to assume that this is a uniform magnetic field. So this is B. Right. Okay, I tried to draw these crosses with equal density, right? And we have a particle. Positive particle enters this structure. Okay, let me draw another line of crosses. Right. Enters this magnetic field over here, for example. So we have positive particle plus Q enters this way, V, right? And we need to describe what is this particle going to do. Okay. So magnetic force, of course, since we have charge exposed to the magnetic field, there must be magnetic force. So let's recall the formula again. F equals QV B, right? Again, every time, in order to find direction of the force, first find the direction of V cross B, and then quickly check. If the sign is positive, then this direction is going to give us direction of the force. But if charge is negative, then this direction must be flipped in order to find the correct direction for the force. Okay, charge is positive, so no troubles. We just need to find the direction of the cross product of V and B. V, that way. B is into the board, so right hand rule number 1, how to find the direction of the cross product. V cross B, B is into the board, right? You see, into the board, V cross B, and the my outstretched thumb gives me direction of the force. So the force will be up. Magnetic force will be in this direction. So that's direction of the magnetic force. Maybe I should add the subscript M, right? Magnetic force. So as a result, we have force perpendicular to the direction of motion. We're going to have cyclotron motion. So this particle is going to experience a circular motion, right? Circular motion. All right, so I can draw something like this, right? Of course, if magnetic field goes almost to that infinity, so we're going to have a circular motion, right? And of course, if the magnetic field ends over here, so it will travel along the circle to this point, and then it will travel straight, right? But if you assume that magnetic field extends all the way to that infinity, so we're going to have circular motion. So we're going to have cyclotron motion. Again, if you want to find this radius of the cyclotron motion, you can apply Newton's second law or just use the formula. You can find the period and so on, right? Okay, so that's part A. So part B, again, uniform magnetic field, but now let's assume that the magnetic field is out of the board. So out of the board dots are used, right, to show that direction. So dot, 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 dot. Okay, it's getting tedious. Okay, enough. So these are our magnetic field lines. And again, particle. Let's assume that we have negatively charged particle over here. So minus charge Q, right? And it enters magnetic field this way. So that's the velocity V. And again, we need to describe the motion and what will be the direction of motion and so on. Again, physics is very simple. We have a charge exposed to the magnetic field. There must be magnetic force, Lorentz force, right? F equals Q V cross B, right? Again, in order to find direction of this force, first direction of V cross B. V is up, B is towards you, right? B is towards you. So in order to find the cross product V cross B, V up, I have to position my hand like this so that I can bend my fingers towards the second vector in the cross product B. So V cross B, and my outstretched thumb gives me this direction. So okay, that way. So, but that is, let me use different color. So that's the direction of V cross B. But we have a second step, small step, right? Check the sign of the charge. Here the charge was positive, so direction of V cross B gave us direction of the force. But now V cross B that way, but charge is negative. Charge is negative, so in order to find direction of the force, we need to flip this direction. So actual direction of the force is going to be this way. So this will be FM. So that's the direction of the force. So particle tries to travel straight, but because of this magnetic force, particle is going to experience circular motion, cyclotron motion. So we're going to have something like this, right? Again, if you assume that magnetic field extends all the way to that infinity, so there will be a circle and extends to that infinity, so there will be just a circular motion. But if magnetic field ends over here, so it will complete this quarter of the circle and then will move straight. But within the magnetic field, particle is going to experience circular motion. So again, I can sort of show that this is again cyclotron motion. And again, be careful about the sign of the charge. Every time check that. Okay, that's enough for today, and thank you, and I'll see you next time.